Okay, today we are going to do some problem solving for the active filter part. Okay, I haven't posted this yet, but you go through them and I will post them today, okay? So just take notes now and I will post them right after the lecture. So today is just problem solving about active filters. Just to like train yourself on how to solve these problems, similar problems in the final exam, okay? Before we start, do you have any questions about the active filters? Remember that we this was the lecture. These were the notes of the active filter. We talked about, you know, the various types of filters: low pass filter, high pass filter, band pass filter, band stop filter, all pass filter. And we talked about how to realize them in certain approximation responses, like Butterworth, Chebyshev, inverse Chebyshev, elliptic, and Bissell. And we studied how they look like in terms of the pass band and the stop band and the transition frequency range. We also studied how to design a first order stage, okay, which is going to be Butterworth because you cannot have any ripple in a first order stage, whether it's low pass filter, high pass filter, and so on. And the most important part is how to find the frequency response. Given a circuit like this, how you find H of S, which is V out of S divided by V in of S. So you need to use the KCL, KVL methods to find out the transfer function, okay? And also from this transfer function, you find the cutoff frequency, bandwidth, quality factor Q, and so on. This is for the first order, and these are some examples. Second order is will have a transfer function look like this one. You know, this is the frequency response. Has different Qs. If Q is less than 1, you will have no notch here or no peak, okay? No resonance, so you don't have any resonant frequency. But if Q is larger than 1, you will start having a peak here, and this peak has a gain of Q times H0, okay? And this peak, you know, the frequency of the peak is not exactly at the corner frequency, it's a little bit to the left, okay, depending on how high this peak is. If the peak is very high, then omega 0 and omega peak, or we call it omega resonance sometimes, they will be almost the same. But if the peak or Q is not that high, so there will be a slight difference or shift between omega peak or omega resonance and omega 0. And as we mentioned before, the second order Butterworth has a Q of 1 over square root of 2, so it's 0.707, okay? And this is the general form of a second order filter, and we can realize this filter using one of these 4 circuits, okay? So now we have a filter type, so try to remember this. You have a filter type, and that means low pass filter, high pass filter, band pass filter, and so on. You have an approximation realization or approximation type, and this is Butterworth, Chebyshev 1, Chebyshev 2, Bissell, and elliptic, okay? And we have a circuit to implement, a circuit realization, okay? So this is the circuit type you implement any of these filters. And we have studied 4 of them: Salenki, Friends, which is the multiple feedback filter, Thomas, which is the multiple op-amp by quads, and KHN, which is sometimes called state variable filter. And these are the different types of filters and the general transfer function of each type. So for a low pass filter, you will have this general transfer function where you don't have any S in the numerator. For the high pass filter, you have S square. So all of them have the same denominator, but the numerator is the one that distinguishes between low pass filter, high pass filter, and so on. So if you have S only, this is a band pass filter, and a coefficient, of course. If you have S squared plus constant, this is a band stop filter. If you have almost the same numerator and the denominator are almost the same except for a negative sign, this is an all pass filter and is used to compensate for the phase. And we focused on the low pass filter because low pass filter is the designing low pass filter is the key circuit that you can use it to design any other filter. Okay, so this is the general low pass filter transfer function. The main important parameters here are the H0, omega 0, and Q. So designing a low pass filter means that you know H0, how much is H0, how much is omega 0, and how much is Q. Okay, and as I mentioned for Butterworth, Q is 0.707. So if the question asks you to design a Butterworth second order filter, then you choose Q as 0.707 and use it for the design. Okay, now we have to know how to find the transfer function of a circuit like this. Okay, so I think we covered this for Sallen-Key. We covered it also for the French circuit, and we covered it for Thomas circuit. And the final one, I asked you to do it as an exercise. Okay. Any question before we go through the problem set number 6? Okay, so this is the problem set number 6. Okay, so I will just show you how to solve them. I'm not gonna solve every question till the end. I'm just gonna give you the key to the answer, and you can finish it at home. Okay, and you let me know if you have a question. Okay, so the first one talks about a second order filter that has two poles at S equals -½ plus or minus j square root of 3/2. Okay, so we have two poles. Okay, and the other requirement, the transfer function is 0. So h of s is 0 at omega equals 2. And 2 radian per second, and it is unity. So the transfer function also has a unity gain at DC. So when omega is 0, then the transfer function or the frequency response is 1. Find the transfer function. So we need to find the transfer function. Okay. So let me go ahead here. Sorry. I don't know how to. Is there a way to show the whiteboard or a blackboard or something here? I think, yeah, I have to stop sharing here now. And then I share whiteboard. Okay, can you see the whiteboard now?
Yes.
Yes, okay. So we need to design, just a second. So we need to design a second order filter. So it's a second order filter. Okay, second. Oops. Let me change this to another color. So it's a second order filter. Oops. So it's a second order filter. And you have P1 and 2. They are located at S equals negative half plus or minus J square root of 3 over 2. Okay, so you have two poles. Okay, if you plot the S plane, so this is the S plane. Okay, so this is the real part and this is the imaginary part. So at real part is minus half. Okay, and imaginary part of square root of 3 divided by 2, you have a pole here. And of course, if you have an imaginary pole, you have to have the other one here. Okay, so the complex conjugate at negative square root of 3 divided by 2. Okay, so this is the S plane. Okay. Okay, so this is second information. Next, we have a Z1 at omega equals 2 radian per second. And you have H of 0 means that at omega equals 0, you have H of 0 equals 1. We need to find H of S. Okay. Well, since this is a second order filter, then we can write the general form of the transfer function as this. So this K, and since you have two poles, so it's S minus P1 times S minus P2. This is Z2, Z1 and Z2. Okay, so this is Z1 and this is Z2. So S minus Z1 minus Z2 divided by S minus P1 times S minus P2. So this is the general form of the second order transfer function with two zeros and two poles. Okay. We know that we have 1 0 at omega equals 2 and 1 0 at omega equals 0. Okay, or the H of 0 is 1. Okay, so let's find, now we need to find Z1 and Z2 because we know P1 and P2. So we need to find Z1 and Z2. Okay, we say that for S minus Z1, so this is the first 0. How to know the value of Z1 here? We know it from this information, piece of information here. Okay, at omega equals 2, we have a 0. Okay, well, if you convert this one into the frequency domain, you have j omega, because we know at the frequency domain, S is j omega. So minus Z1 equals 0, right? Because this is a 0, right? So in this case, this is a 0. So we have to equate this with 0 and substituting at omega equals 2 radian per second. Okay, so if you substitute omega as 2, this gives you 2 J2 minus Z1 equals 0. And from this, you can say that Z1 is J2 or 2J. Okay, so if you solve this for Z1, you're going to get Z1 equals J2. Okay, so you have a 0 at J2. So if you have the J2 here, for example, is here. So you have a 0 here. Then you should have another 0 at -2. So this is at 2. Then you have another 0 at -2. Okay. So that means Z2 is negative J2. Why is that? Because any complex pole or 0 has to have its complex conjugate with it. Okay, so here we have -12 plus j square root of 3 over 2. Then we should have -12 minus j square root of 3 over 2. So if you have one pole here, then you have to have the other one, the other mirror one, or the other complex conjugate one as well. You cannot have one complex pole or one complex 0 and that's it. Complex poles and zeros, they appear in pairs, in complex conjugate pairs. So once we know that Z1 is plus J2 and this is complex, then Z2 has to be also minus J2, okay? So that means H of S now equals K times S minus Z1, which is S minus J2, times S minus Z2, which is plus J2, okay, divided by S minus P1. I'm not going to write it here because it's a big one, but just we'll simplify this first. And S minus the complex conjugate of P1, because P1 and P2 are complex conjugates, right? So we can write this one as P1 complex conjugate, right? Okay. Now, if you simplify the one on the top, okay, if you multiply this by this, or you can just simply say that this is the difference between two squares, right? S minus A times S plus A means S square minus A square, right? So this is S square minus J2 all square, right? If you have these two factors multiplied to one with minus sign and one with plus sign, this is the difference between two squares. So this is S square minus J2 square. And this one here, you can do it by yourself, is going to be S square, okay? If you substitute B1 and P1 conjugate, this is going to be S square plus S plus 1, okay? So do it by yourself, substitute P1 with this value here, and substitute S2, B1 conjugate with the other value, and you will get this value here, okay? So that means this equals K times S square, okay? J2 square, J square is -1, multiplied by this negative is going to be positive, and 2 square is 4, okay? And the denominator is going to be S square plus S plus 1, okay? So now we found the transfer function. All what we need is to find how much is K, okay? How much is K, okay? Any question before I delete this page? Okay. So now we have H of S is K times S plus 4, S squared plus 4, divided by S squared plus S plus 1. Okay, how to find K? What information that we use to find K? If you go back to the question, I don't think, can you see the Word file now, or still see the board? Hello?
Can't see anything on the screen.
Okay. So I will share this one here. Can you see the Word file now?
Yes.
Okay. So we already used the pole locations, the two pole location, and we used the frequency too. And the only information that we haven't used yet is the unity gain, okay? So how can we use the unity gain to find K? Remember that we said that H of S equals K times S squared plus 4 divided by S squared plus S plus 1. How can we use this information to find K? Any answer? What does it mean omega equals 0? What does it mean in the S domain? If omega is 0, how much is S?
0.
0. So H of 0, so omega equals 0 means S also equals 0, right? Because S is j omega, right? So omega is 0, then S is also 0. So H of 0 equals how much? Equals 1, right? And this means equals K, and we substitute S with 0 because S here is 0. So this is 0 plus 4 divided by 0 plus 0 plus 1. So that means 4 over 1 times K, so this is 4K, right? So 4K equals 1, that means K equals 1 over 4. Okay? So we use this information to solve for K because it says that unity gain, the gain is unity at DC. At DC means omega is 0, no frequency. When omega is 0, then S is 0. So we substitute S as 0 here and we replace this with 1. So we get this value of K. Okay. So I don't know how to switch faster between these things. Okay. So we said that, I'm going to repeat this again, H of 0 equals 1 equals K times 0 plus 4 divided by 0 plus 0 plus 1. Okay. And this is equals 4K. From this, we can say that K is 1 over 4. So the final transfer function in this case is going to be 1 over 4 S squared plus 4 divided by S squared plus S plus 1. So this is the final answer of this quiz. Okay. So this is the solution for the first question. Any question about this? So by giving some information about the location of poles and zeros, about the transfer function at certain frequencies, you can write the transfer function or the frequency response of the whole field. Okay, so this is the main idea of this question. Okay. Any question? Okay, so let's move to the second one. So the second question is asking you to design okay, just give me a second, just a second. Sorry about that. Okay. So the second question is a design question. It's asking you to design a second order Butterworth filter. Okay, so second order Butterworth low pass filter. So these are three important informations here. So second order and Butterworth and low pass filter. Okay, the 3 decibel bandwidth. So this is the cutoff frequency, or the 3 decibel frequency, is 10 kilohertz. Okay, so so this is F0 equals 10 kilohertz. Okay, or FC or F0. And the DC gain is unity. Again, what do you mean? What do you understand from this information? The DC gain is unity, means that H of 0 is 1, right? When omega is 0, that means S is 0, so H of 0 is 1. We need to use a Sallen-Key circuit with 10 kilo ohm value for all resistors. So R used equal R's with 10 kilo ohm. So we need to design a Sallen-Key, or to realize this Butterworth filter using a Sallen-Key circuit with R's equal 10 kilo ohm. Okay, so let's go ahead and try to utilize all this information to design the circuit. So if you remember, the Sallen-Key filter is usually like this. If you remember from the notes, the Sallen-Key filter has the gain in this side, which is Ry over Rx. But since the gain is unity, then we have to have a unity gain. So unity gain means you connect it this way, right? Okay, and from the other side, we connect the filter. So you have two capacitors, one of them here, okay, and you have a resistor here. You connect this one in between, and then the other resistor is here, okay. Let me just simply modify this a little bit. So this is the unity gain, and we have another capacitor here, okay. So this is the Sallen-Key circuit, okay, and this is Vn, this is V out, and this is, now we have equal R, so we have this is as R, and this one is as R also, and this is C1, and this is C2. So we need to design this circuit based on the following information. So we know that H0, which is the same as H of 0, by the way, which is K, which is 1 in this case. Okay, so the feedback here is 1. And since it's a Butterworth, what does this mean in terms of Q? Okay, remember for Butterworth, how much is Q?
.707.
0.707, or 1 over square root of 2. Okay, so this is the same thing, 0.707. Okay, oops. So from the word Butterworth, we know that the Q factor, or Q quality factor here, is 1 over square root of 2. Okay, if you go back to the slides, okay, and see the design equations, one of the design equations was that Q equals half square root of C1 over C2, okay, and the other design equation, that omega naught is 1 over R times C1 C2. In the case when R1 equals R2, this was the two design equations if you go back to the slides, okay. So the design here means to find C1 and C2 because these are the two unknowns. The circuit now is here and we know R's, but we don't know C1 and C2. So we need two equations to find C1 and C2. And these are the two equations, right? So we say that here 1 over square root of 2 equals half square root of C1 over C2. And this is equation number 1. And from this one here, we know that F0 is 10K. So we say that 2 pi times 10K, which is 10 to the power 4, equals 1 over R is 10K. So this is also 10 to the power 4 square root of C1, C2. And this is equation number 2. You solve 1 and 2 to find. So solve 1 and 2 to find C1 and C2. Okay. So, and this is what meant by the design. Okay. So design is to find all the components of this Sallen-Key circuit that satisfies the conditions given in the question. Okay. Any question about this? If no question, does it mean it's very clear or it's not clear at all? Okay, I assume everything is clear. So when we move on, so let me stop this and go back to the Word file. Okay. So the third question is, and you have to expect something like this in the exam, you know, like you need to find the transfer function of a circuit. I'll give you a circuit like this, or like this one, or like this one, and I ask you to find the transfer function of the circuit. So this is why we have many questions here to find the transfer function of them. Okay. So this is one way to find the transfer function of a filter, right? So given this circuit here, question 3, given this circuit, we need to derive the expression for the voltage transfer function. Okay, so we need to find V out of S divided by Vn of S. So this is what meant by the transfer function. Okay, so here we need to find H of S, which is V out of S divided by Vn of S. Okay. And the second question, what is the type of this filter? So that means, is it low pass filter, high pass filter, and so on. So we choose what type is this. Okay. So remember that there is a type, which means low pass filter, high pass filter, and so on. There's an approximation, which means Butterworth, Chebyshev, and so on. And there's a realization circuit, whether it's Sallen-Key or a different circuit. Of course, this is not one of the common circuits that we have studied so far. So this is not one of the circuits that we already studied. Okay, but it's a second order because it has these two capacitors. So it's a second order filter. And we need to realize to figure out, is it a low pass filter, high pass filter, and so on. Okay, what do you think? If you look at this circuit, what do you think? Do you think this is a low pass filter, high pass filter, or what? Before we do the analysis or the math, can you look at this circuit and quickly realize whether it's a low pass filter or high pass filter or what? Like by looking at these two capacitors and finding when omega goes to 0, what's going to happen, and when omega goes to infinity, what's going to happen?
Does VI get blocked at omega equal to 0?
Sorry, say it again.
Is there a low pass filter in that first part? Sorry, a high pass.
Okay, let's see when omega goes to 0, right? It's a very low frequency, okay? When omega goes to 0, this is going to be open circuit, and this is going to be open circuit, right? Now, what do you think of the output would be? If this is open circuit and this is open circuit.
0.
0, right? Why? Because there's no input, right? You didn't apply any input, right?
Yeah.
You open circuit the input, so no input, so the output is 0, right? This is open circuited, and this V minus is the same as V plus, and this is 0, and no current here. So because there's no current here, so there will be no current here, so the output will be 0, right? Now let's think about omega goes to infinity, very high frequency. We know that the capacitor acts like short circuit in high frequency. So this is going to be short circuit, and this is going to be short circuited. So what do you think the output will be?
R2 over R1.
This is short circuit.
Oh, okay.
So R2 parallel with short circuit is 0, right? The short circuit wins here. So you have a short circuit here. So the output is short circuited to this point here. There's no effect of R2 in this case. So the output is also 0, right? Because the output is short circuit to the inverting terminal, and the inverting terminal, as we know, V minus is approximately equal V plus. There is a virtual connection here. So if this is ground, this is also approximately ground, virtual ground. So V out now is connected to the ground. So V out is 0. So in a very low frequency, the output is 0. In a very high frequency, the output is also 0. But in between, the C2 and C1 will have some impedances. You know, this C2 impedance will be added parallel to R2, and this C1 impedance will be added series to R1. So there is some impedance, you know, like if you divide R2 over R1 or Z2 over Z1, you will get some values. So we would think of the transfer function or the frequency response to be something like this. At low frequency, it is 0. At high frequency, it's also 0, but in between, there is something here. Okay. So this is a bandpass filter for sure. Okay. And we will prove this right now. Okay. So we need to find the transfer function. We need to find the type of the filter. And finally, if we have R1 is this, how much is R2, C1, C2? We need to design it. If we know that R1 is, if we're going to select R1 as 10K, how to find R2, C1, C2 to give a mid-band gain of 50. Okay. And a cutoff frequency, 2 cutoff frequencies, because this is a bandpass filter, so you have 2 cutoff frequencies. So you have omega 1 here and omega 2 here. Okay. So let's do this. Okay. So I will draw the circuit here again. I have a capacitor here, a resistor, and a resistor here parallel to a capacitor. So this is C2, R2, R1, C1. This is minus, this is plus, and this is the ground, and this is V out, and this is V in. Now, how can we find H of S? How to start? Well, we know that if you have a feedback, a negative feedback structure like this, okay, this is a general analysis thing. So if you have a Z2 here and a Z1 here and Vn here and V out here, what's the transfer function of this filter or this system?
Minus Z2 over Z1.
That's correct. So H of S equals V out of S over Vn of S, which is minus Z2 over Z1. Now, how much is Z1? If you look here, so this is Z1.
R plus 1
R1 plus
1 over S.
1 over SC1, right? Which is 1 over J omega 1, omega C1. But we're going to use S instead of J omega, okay? Now, how about Z2? How much is Z2? So Z1 is the series combination of R1 and C1, and Z2 is
The parallel.
parallel combination. So it's R2 parallel to 1 over SC2, right? We can write this in a different way. Instead of multiplying and dividing, we can write this as 1 over Z2 equals R2 plus, not R2. One over R2 using the reciprocal form, okay? So since they are parallel, so the reciprocal of the equivalent impedance equals the reciprocal of the first impedance plus the reciprocal of the second impedance. So the first impedance is R2, so the reciprocal is 1 over R2. The second impedance is 1 over SC2, so the reciprocal is SC2, okay? So we can use it this way. And we can write this one here as negative 1 over Z1 times 1 over Z2, okay? Is it the same? You know, this one is the same as this one, but just I moved Z2 to the denominator by 1 over Z2 because we define Z2 this 1 over Z2 this way. So we can say that H of S equals 1 over, how much is Z1? It's R1 plus 1 over SC1, which is this one here. And how much is Z2? 1 over Z2, it's 1 over R2 plus SC2. Okay? So this is H of S. Okay, now you need to simplify this a little bit. So, of course, there's a negative sign here. So you can take R1 and 1 over R2 common outside these factors. So you will end up with negative, and you have here R1 common divided by R2 also common. Okay, take them common. And from the first factor, you will have 1 plus 1 over SC1 R1. Okay, and the second factor, if you take 1 over R2 outside, you will end up with 1 plus SC2 R2. Okay, so from here you take R1 common, from here you take 1 over R2 outside, then we are left with 1 plus 1 over SC1 R1, and here 1 plus SC2 R2. Okay, just you can check by multiplying R1 here and R2 here, 1 over R2 here, you get the same thing. Okay. So I will write it again here. So we know that H of S equals 1 over 1, okay, minus R1 over R2 times 1 plus 1 over SC1 times 1 plus SC1 R1 SC2 R2. Okay, so that means this is going to be minus R2 over R1 times 1 over the two factors here. Okay, so if you just move this to the top, it's going to be R2 over R1 instead of R1 over R2. Now let R2 over R1 becomes the K, the gain, or the midband gain. Actually, this is the midband gain. Okay, and let's define omega 1, which is the first cutoff frequency, or the low cutoff frequency, as 1 over C1 R1, and we define omega 2 as 1 over C2 R2. Okay, so this transfer function could be simplified as H of S equals minus K divided by 1 plus omega 1 over S times 1 plus S over omega 2. Is that correct? Please let me know if I'm missing something or I. So here I just assume that omega 1 is 1 over C1 R1, omega 2 is 1 over C2 R2, and I substituted omega 1 here and omega 2 here. Okay, so I removed 1 over C1 R1 and replaced it with omega 1 here. So you have omega 1 over S, and I substituted omega 2. I replaced 1 over C2 R2, so this is going to be 1 over omega 2, right? So it's S over omega 2. And K is R2 over R1 with the negative sign. Okay. We can try to put this in the standard form, you know, to know the filter type. Okay, if you go back, let me stop this one here for a moment, and then go back to the slides here. Okay, if you go back here, yeah, these are the standard forms of a second order filter. So we need to put our transfer function in one of these forms. And we see the numerator. If we have just a constant, then it's a low pass filter. A constant times S squared, then it's a high pass filter, and so on. But we have to put the denominator in this form, S squared plus constant times S plus constant. And we see the numerator shape. If it's this shape, then it's a low pass filter. If this shape, high pass filter, and so on. Okay, so let's go back and try to put our transfer function in the standard form. Okay, so how to do this? Simply we can multiply both numerator and denominator by omega 1, by 1 over omega 1. But we have to multiply it by S here, so we need to multiply by S here to get to make this here, and we have to multiply this by omega 2. So we multiply by S times omega 2. So this becomes, so I multiply here, let me change the color. So I multiply by S omega 2 divided by S omega 2, okay? Both sides by S omega 2. So this is not going to change anything, but going to simplify it or put it in the standard form. So that means if you multiply the numerator by S omega 2, this is going to give you minus K omega 2 times S, okay? Divided by S here, if you multiply this S by this factor and omega 2 by this factor, so it's going to be S plus omega 1 times, if you multiply omega 2 by this factor, you're going to get S plus omega 2, right? If you multiply these two factors, you're going to get minus K omega 2 S divided by S squared plus, okay, now I multiply omega 1 by S, omega 2 by S, so this is going to be, oh, sorry, this is 1 over omega 2, right? Or is that correct, or this is, no, actually this is correct. No, it was correct. If you multiply omega 2 here, so this is going to be S plus omega 2, right? Right, so this is omega 1 plus omega 2 times S plus omega 1 times omega 2. So now we put it in the standard form, and we will notice in this standard form that we have a factor of, like an S variable here in the numerator. So that means this is a band pass filter, right? If you go back to the standard forms, you find if you have S on the numerator, that means it's a band pass filter. And we already proved this before we started the analysis, okay? Okay, so that tells us it's a band pass filter. And the next part was to find if we have R1 equals 10K, how much is C1, C2, and R2? Okay, so let me clear this. So the next part says that you have R1 is 10K, and also A midband equals 50. Okay, so this is part C. Okay, and the question is to find C1, C2, and R2. Okay, that makes these values. Okay, so I'm gonna write. So what equations we use to find out, and also you are given also the two cutoff frequencies. So F1 is 200 hertz, and F2 is 500 hertz. So how can we use this information to find out how much is C1, C2, and R2?
You can use the frequency equation, F equals 1 over 2 pi RC.
That's correct. So remember that omega 1 equals 1 over R1C1, right? And we know that omega 1 is 2 pi F1. So this is 2 pi F1, right? So if we substitute F1, you substitute R1, then you find C1. So from here, we can find C1. Okay. Now, we can also use omega 2, but we are not gonna get anything because in omega 2, we don't know how much R2 is and how much is C2 is. So we have two unknowns. So we have to find R2 before we go to the second frequency. How to find R2? Remember how much is the midband gain? As a magnitude, forget about the sign.
Can it be minus K equals to R1 over R2? A midband equals to minus R2 over R1.
No, in the midband, you assume that the two capacitors are not working. So you have a resistor here and another capacitor here and a capacitor here, okay? And a capacitor here and a resistor here, right? And this is R1 and this is R2, okay? So if you assume that this capacitor is short circuit and this capacitor is open circuit, then you will have the gain as negative R2 over R1. So this is R2 over R1, right? So the midband gain, the frequency is too high for C1 and too low for C2, okay? C1 mid frequency, if you are in the mid band here, so this frequency here, omega mid band, it's in the middle, or omega 0, it's in the middle. So this frequency here is very high for the capacitor C1, so it's considered as short-circuited, and it's very low for the capacitor C2, so it's considered as open circuit. So if C2 is open circuit and C1 is short-circuited, then the gain is R2 over R1. So this is the mid-band gain. Okay, so this is 50. And we know that R1 is 10K, so from this one, we can find R2. Okay. Now we can go back to omega 2. Omega 2 is 1 over R2 C2. And we know now omega 2, we know R2, then we can find C2. Okay. Any questions? Okay, so let's go back to the someone is asking, do we have to simplify to standard form, or can we stop here? I'm not sure what here is referred to, but do you mean this question or the previous one? Or I think this one we simplified it to the standard form to figure out the type of the filter, because the question was, let me share the question again. So the question here was, what is the type of this filter? So we need to find the type of this filter. Is it low pass, high pass, and so on? Okay. You can sometimes find it from the circuit, as we said, but it's easier to simplify the transfer function to the standard form and tell from the standard form that this is a low pass filter or high pass filter or band pass filter and so on. Okay. So it's, yes, it's better. It's a good idea to simplify it or to put it in the standard form. Okay, let's go to the next one. We have this circuit. Okay, it's not clear whether it's a Sallen-Key or a different circuit or multiple feedback. It looks like more multiple feedback circuit, but it doesn't matter. We don't ask about the type of circuit here. The only thing we're asking here is to find H of S, which is V out of S divided by Vn of S. Okay, so how to find the transfer function of this circuit? Do you remember the method that we used in the lecture to find the transfer function? If you remember, we said we have to use KCL. Okay, so we need to label these nodes, like we can call this node as A, this one A, and this node as B, and this node as C. Okay, CAB, right? And we do KCL at nodes A, B, and C. Okay, so we label the nodes with some letters, and we start doing KCL at A, B, C, right? Okay, so let's do this. Okay, we're talking about the previous question. Let me go back to the previous question. You mean this one, question 3 or question 2? Okay, what I was talking about was question 3. So this is the one. If you mean that this is the previous question, okay, just let me know. So let's go back and share the whiteboard. Okay, that's good. So let's share the whiteboard. and move this a little bit. Okay, so I will redraw the circuit again. So this is the circuit, and we have a resistor here. This is the negative terminal, this is the positive one. The positive one is connected to the ground through R1. Actually, all of them are R, okay? So the good thing is that all resistors are the same. So this is R, this is R. And you have a capacitor here. We call it C1. And another capacitor here. We call it C2. And this capacitor is connected here. And this two capacitors are connected to a resistor R. And another resistor R here. And these two together are connected. And this is R. And this is Vn. And this is V out. Okay, and remember that we labeled this as A here, and we labeled this as B, and we labeled this point at C. Okay, so let's now do the KCL at each of these points. So start KCL at node A. Okay, so how to do KCL at node A? Someone tell me. The summation of all currents is 0.
Can it be A minus V input
VA,
minus V input?
V input?
Yeah, over
You go
R.
from here to all the way here. You know, how much is the current through C2?
Oh, okay.
How much is the current here?
That's VA to VB over C2.
VA minus VB
VB
over?
C2.
No, C2 is not a resistance.
Sorry.
What's the impedance of the capacitor?
Can it be 0 minus J something?
1 over
SC?
SC.
2. Oh,
Okay, so this is not C2. This is the impedance of C2. We don't divide voltage by capacitance to get current. We divide voltage by impedance. Okay, and the impedance of C2 is 1 over SC2, right? Okay, then
noted.
plus, what's the other current? How many currents here we have at A? This is 1, and the other one is this one here, right? Do we have any current here?
No.
No, so this is 0, right? So we have 2 currents, one here and one here. This is the first one. How much is the second one? How much is the current through R? This feedback R.
That's VA minus V0 over R.
That's correct. And this equals
0.
So we can say that VA minus VB times, okay, if you move this up, SC2 plus VA minus V0 or V out times 1 over R equals 0, and this is equation number 1. Okay. Can someone give me the KCL at node B? How many currents here? Well, we have a current here.
That's VB.
Let me just delete these currents now. Oops. Okay, so how many currents we have now?
That's
One current here, one current here, and one current here, right? So, okay, so what's the first one? Let's start with this one here. C2.
That's VB minus VA
VB minus VA divided by
over 1 over SC2.
SC2. Yeah. So this one is the same as this one, but with switching B and A, right? Okay, what's the current? The other current? Someone else.
VB minus V input
Yeah, VB minus V input
over R.
divided by R. How about the third one?
VB minus V output over
V minus V output divided by R equals 0.
Is it R or C 1 over C1? 1 over
Sorry,
S1.
yeah. Sorry. Yeah, this is not R. This is 1 over SC1. Okay. So you can simplify this as VB minus VA times SC2 plus 1 over R times VB minus V input plus VB minus V out times SC1 equals 0. And this is equation number 2. Okay. And you do the same thing for node C. So this is C. Okay. So how about node C? So I'll delete this one here and delete this. Okay, how about node C? At node C. So we have two currents now. So if you just delete the currents, so delete this one, delete this one, delete this one. We have one current here, and we have one current here. Do we have any current this way?
No.
We don't have any current in the plus input, right? So we can write this as VC over R. Okay, so this is this current here. VC minus 0 over R plus, what's the second current? VC minus Vn over R equals 0. Okay, so this is equation number 3. So how many unknowns we have here now? If we substitute between A, B, and C, look, I mean 1, 2, and 3, we will still have one unknown in the equation other than VI and V out, right? So we need to have another equation to get rid of these variables. You know, we need to mix equation 1 that was here, and I deleted it, equation 2, equation 3, to come up with one equation that links V input and V output only. We have to get rid of VC, VB, VA, and so on, and we just keep V input and V and V output. Okay. So we can use the other equation, or don't forget this equation that VA equals VC, right? Because in the operation amplifier, the two inputs are virtually connected. So VA and VC are the same. So this is equation number 4. So use 1, 2, 3, and 4 to combine them to come up with a certain equation. I know it's not easy. It's going to take time. mixing these equations, but try to train yourself how to do them. Like try to simplify them as much as you can. But anyway, like if you put these equations, that's enough. You know, like that's more than enough. I know that mixing them is not easy, and you might commit mistakes in this, but at least you have to know how to write these node equations, the node KCL equations. Okay. So try to simplify it and let me know how do you find the final transfer function, and whether what kind of filter you will get. Is it a low pass filter, high pass filter? Based on try to put it in the standard form and look at the equation and see which type of filter you have. Okay. Any question? Okay. Let's go back to the okay. Question number 5, you already have the transfer function. I gave you the transfer function. It's not a circuit and you find the transfer function. The transfer function is already given. Okay. And you have 3 questions about this transfer function. So as you can see, the transfer function is a second order with some parameters R, RQ, R2, C, and so on. And the first question is to find expressions for H0, omega 0, and Q. So how can we find an expression for H0, omega 0, and Q? Of course, in terms of the R's and C. So any idea how to find these? How to find these expressions? First of all, is this transfer function in the standard form?
Yes.
Everybody agrees?
Is that not a low pass filter?
No. First of all, it's not in the standard form. If you go back to the standard form, I'll show you the standard form. So these are the standard forms. Okay. These are the standard form. So look at the denominator here. Always the coefficient of S square has to be 1. You always have to have 1 here. Okay. So always here, this is 1. Okay. Always this is 1. You have to keep this as 1. In the standard form, forget about the numerator, but the denominator, the coefficient of S square has to be 1. If we go back to the question, you will find the coefficient of S square is not 1, right? So we have to convert this to the standard form. How? So we have to divide
By coefficient of S squared.
Exactly. Divide by RQ, R2, R square, C square, both sides, okay? Both D of S and N of S, numerator and denominator of S, okay? So we call this the numerator of S, and we call this the denominator of S. Okay, so you have to divide both of them by this one. Okay, so first of all, you divide by this, and you're gonna put it in the standard form. Once you put it in the standard form, okay, you can equate each coefficient with the standard form coefficient. Okay, so let me show you how to do this quickly. So if you go back here, So this is the standard form, and you will find it. It's a low-pass filter. That's correct because it doesn't have S in the numerator. So the coefficient of the S term is omega 0 over Q. The free term is omega 0 square. Okay. So let me how to do this. Stop and then share. Okay. So if you do this, you will find H of S equals R over R2 times 1 over R square C square divided by S square plus 1 over RC times R over RQ times S plus 1 over R square C square. So from this, if you compare it to the standard form, which is H0 omega naught square divided by S square plus omega naught over Q S plus omega naught square. From this, you can say that how much is omega naught? Is the square root of this part here, right? So it's 1 over RC. How much is omega naught over Q? It's 1 over RC times R over RQ. And this equals 1 over RC divided by Q. So from here, you can find Q, right? And Q is going to be RQ over R. And how to find H0? H0 is this factor here that's multiplied by omega 0 square, which is R over R2. Okay, so that's it. So these are the expressions for omega naught, for Q, and H0. Okay. And finally, you need to substitute the values C with 20 nanofarads and to find R, R2, RQ. That gives you H0 equals 2, Q equals 2.5, and omega naught equals 2000 radian per second. Okay, so use the values and plug them in for H0, for Q, for omega naught, and find the corresponding R, R2, and RQ. Okay. And the third part is to sketch the transfer function. Okay. So this is a low-pass filter, right? We said this is a low-pass filter. Does it have a peak value or not? Based on the values here for this part B. So based on this, does the filter, so we know that it's going to be a low-pass filter, right? So it's going to be something like this. But does it go smooth like this, or does it have a peak here? Based on these values here, or these. It does have a peak because Q is greater than 1. Q is greater than 1. And as I mentioned in the lecture, if Q is greater than 1, you will have a peak. If Q is less than 1, actually less than 0.707 or 1 over square root of 2, you will never have a peak here. So since Q is 2.5, you will have a peak. And the value of this peak is, here, all this height here is Q times H0, okay? So the value of this peak is this, but in dB, okay? You have to convert it into dB. You multiply Q by H0, this is Q and this is H0, and convert it into dBs. And the value here is H0, right, in dB. Okay, so to try to plot this transfer function and see the frequency response, how it look like giving these values, okay? So that's it. I think the next one is similar to this one. You can do it by yourself. This one here, okay, this one here, it's the same thing. And this one is easy. Just do the transfer function again and find all these values. You know, what kind of approximation is this, and what's the corner frequency or the pole frequency of this circuit, and how much is the Q value. Okay, so I think by knowing how to solve these ones, you can easily solve the last two ones. Okay, do you have any questions? Okay, I'm gonna go now and post these this problem set. Okay, and go ahead and solve them. They are not required as an assignment, but just try to practice them and let me know if you have any question. Okay, and you have to expect something like this in the final exam regarding this part of the course, like the active filters. You have to know how to find an expression for the transfer function, how to find the parameters h0, q, and omega 0, and how to find, you know, the design a circuit given certain characteristics, as I mentioned. Okay. Okay, thank you so much, and I'll see you in a few hours in the lab. Okay. Thank you so much.